Hi everyone, this is the first of two lectures for, what's the date? October 11th. It's October 11th, so this would be a lecture for October 10th and October 13th. The first things I'm going to talk about are 1 point off of the homework, and then 2 of the topics, and then the second video for what I guess would be Monday the 13th is on another topic, so we're actually going to probably won't make it through that topic completely, but we're going to hit 3 different topics in these 2 videos. First of all, we're almost out of the section of the class where every answer is base width modulation, and we're moving on to the section of the class where almost every answer is loading with sprinkled base width modulations in there. So the beginning of the idea to get you introduced to the idea was this homework problem on Bosco, where Bosco had these 2 voltage dividers. They worked great by themselves. You give it 12 volts, you have 2 resistors here that are equal to each other, so it divides this voltage right in half and you get 6 volts. You have another voltage divider that takes 6 volts as its supply and divides it down to 3 volts, and it worked great. And Bosco said, okay, I'm just going to connect these 2, I'm going to connect this voltage divider's output to the supply of these this voltage divider. Yeah, I mean, this output is 6 volts, the supply here is 6 volts, that should work great. And if you did the math correctly, you saw that that isn't what happened. What happens sometimes is when you're looking at circuits, you look at things as inputs and outputs. You know they're inputs and outputs, but electrons don't. So if you have, let's get, this is supposed to be like the circuit on the homework. We see that as an output. We see that if we put something out here, it doesn't affect this circuit at all. It does. For an electron, it provides another path to flow through. And again, like, we think this is output, so things flowing this way, or things flowing this way, that to us it doesn't look like that happens, but it does. Okay. So when Bosco first tests this out, let's see what happens to current. You have current flowing through here, and you have the same current flowing through here. Okay, that works great. As soon as you put another path over here, okay, so this is the second voltage divider here. What happens is if somebody gave you this in circuits 1 and didn't tell you what was going on here, you'd say that, hey, these 2 things are in parallel. You wouldn't think of this as an output right here. You'd say, oh, these 2 things are in parallel. And that's the way you need to think when you're putting 2 circuits together. If you have one circuit here that works great by itself, one circuit here that works great by itself, when you put it together, all of a sudden this branch of this circuit is in parallel with this branch of, well, the whole circuit here. And all of a sudden your circuit doesn't work the same. What happens here is, now, yes, you still maybe have I going through there. Actually, you don't. But what happens is some I, let's call it I2, ends up going out this way. And now this is actually, whatever that I is, minus I2. And since these 2 currents aren't the same now, so the current through the top resistor isn't the same as the current through the bottom resistor, this voltage right here isn't going to be the same. So once again, if these 2 circuits, if this circuit and this circuit weren't connected, then all of the current through here would also go through there. But as soon as you put a second circuit out here, some of it goes over there, and now you have less going through the bottom, and that's called loading. When you're when whatever circuit you're connecting your first circuit to takes some of your current and changes the behavior of your first circuit, that means your first circuit is loaded by your second circuit, or your second circuit is loading your first circuit. And so this is an important concept, and you'll see it, maybe when you're doing your senior project, you've got two circuits or two chips that you've got, one does one thing, one does another, and you need to connect the output of the first one to the second, and you do, and all of a sudden they stop working. That's loading. And you get down to we can talk about this a little bit more in class, but is the Rn for BJT infinite? No, it's not. Okay, so anytime you make a circuit that creates a voltage that goes to the base of a BJT, that BJT, since it's going to take a little bit of current off your first circuit, so let's try that a little better. So if you have some circuit, some circuit, and whoops, T is funny today, and then you connect it to the base of a BJT. There's some current that goes into that BJT, and your BJT will load your circuit. The trick is to, we haven't talked about how to calculate this again. There's some R out of this. You make R out much smaller than the R in of the BJT. And you've seen in the lab handouts some ways to calculate R in. So you need to make that R in much greater than the R out of your circuit, and then you'll be fine. Okay, so that's loading. Okay, next topic is, it's not much content, but it's like stuff that needs to be said. So let's say it and be done with it. Okay. Let's go to home. Oops, home button isn't working either. Okay. So the third topic is amplifiers, kind of a high-level view of that. All right. So I've said it a couple times, but in this class we don't have time to do every amplifier that exists out there. So we are targeting an op-amp. Op-amp has voltage in, voltage out, but there are amplifiers that have voltage in, voltage out. There's also ones that have current in, current out. They're called current amplifiers. Yeah, the voltage in, voltage out, voltage amplifier. Voltage in, current out, called a transconductance amplifier, and current in, voltage out is a transresistance amplifier. And the way you can figure out what the name is, if you forget whether it's transconductance or transresistance, what you can do is, remember, gain is the output over the input. Actually, the change in output over the change in input. So if the output is voltage and the current is input, if you put the output over input, you get V over I, which has units of resistance. So transresistance. Or this is also called a transimpedance amplifier. This is a little, it's 1 over resistance, or conductance, so that's where the transconductance comes up into play. Also, you can also name your amplifiers as to how many inputs they have or how many outputs they have. So single input, single outputs, differential inputs or outputs. So you could have a differential input, single-ended output. That means 2 inputs, 1 output. Or you can have a single-ended input, differential output, or you can have a differential input, differential output, or you can have single-ended input, single-ended output. And right now, just with what we talked about on the slide, you can name amplifiers in kind of an impressive way. And I would say that now you can go home and say, hey, we're learning something. I just learned how to make a differential input, single-ended output, transconductance amplifier, or something fancy like that. And people will be impressed. I think I've said it a number of times, but gain is a small signal value, so it's a change in something over change in something else. This is one of my pet peeves, that textbooks call gain V out over V in. It's not. It's not. It's not. It's not. It's the change in V out over the change in V in. The only time where it's V out over V in is if the gain goes through the origin, and it's a nice line. And then I guess you can say it's V out over V in. But in that case, if you take delta V out over delta V in, it's still the same thing. But anyways, okay, so gain, small signal value, change in V out over change in V in, various different kind of amplifiers. And if you take all of these names or all of these variations right here, and look at how many different kinds of amplifiers there are out here. We've got a differential input, differential output voltage amplifier. Oops, differential input, and single-ended output, differential input, single-ended output transresistance. You can draw them all up. And that's how many amplifiers we could look at, but again, we are pretty much sticking with this first one right here, voltage in, voltage out, differential input to single-ended output. So that's what the op-amp that we've used looks like. Okay, why would you use an amplifier? You want to amplify something, you want to make it bigger. Microphones, solar explosions, when something's so far away and the signal is so small, you have to have a very, very, very large gain to see the event. But if you have a cell phone, so in other words, for this one, maybe you want close to infinite gain as you possibly can, maybe hundreds of millions or something like that. But for a cell phone or a microphone, you maybe want to amplify it by 2. So first comment here is that we are building an operational amplifier. An ideal operational amplifier amplifies by an infinite, it has an infinite gain, but that's because we're building an operational amplifier. If you were building a different kind of amplifier, maybe you only need a gain of 2, or 1.1, or 10. So don't think that a bigger gain makes it a better amplifier. For our case, yes, because we're building an op-amp, a bigger gain is a better amplifier. But for other applications, a smaller gain, it makes a better amplifier. So there's low noise amplifiers that have a gain of 1 or 2, or 2 or 3 or something like that, and that's for when you have a signal coming off of an antenna. The noise of your circuit, there's intrinsic noise, there's noise that happens just kind of naturally inside circuits. That is, the signal is probably on the order, hopefully a little bit bigger than the noise in your circuit. So in low noise amplifier, it's a technique of designing amplifiers that the internal noise of the circuit is as low as possible, so you can receive as small a signal as possible off an antenna. And that's great, 2 or 3 gain, and now you can use a regular amplifier to amplify the signal up the rest of the way. Okay. So yeah, lots of things you might want to amplify, and again, big gain, we want that because we're building an op-amp, but other applications, there's many reasons for having a lower gain, and in those applications, a lower gain is better than a big gain. So let's look at a couple of interesting things that may have seen, may not have seen. MEMS, micro electromechanical devices. This is you can, in MEMS devices, you can make accelerometers, gyroscopes, actuators, reactors, and for example, it's right here. Yes, it's a capacitor, but it also can sense vibration. Capacitor. ECOs. Okay, for example, let's say, so here it looks like the anchors. What's actually happening here is this plate right here is floating, and these behave kind of like springs. So they're kind of holding up They're kind of holding up this plate, and when the plate is moved, these springs bend a little bit and the plate goes up and down. And if you remember your capacitors, is when the distance changes, the capacitance changes, and current will, if you keep the voltage constant across the plates, as the distance change, current will go on and off of those plates. And watching that current go through a resistor gives you a voltage that you can sense, and tells you how much your circuit's moving, or your MEMS device is moving. That's a small signal. You need to amplify that quite a bit if you want to see it. Here's one plate of the capacitor, and here's another plate. This doesn't look like your regular capacitor, but now when this moves in and out of these two plates right here, now remember another value in your capacitor equation is A for area, so every area of overlap. So if I have something like this, there's a lot of overlap, but as soon as I go to the side, now there's less overlap, and that area decreases. So in the same way as that last MEMS device made current go on and off of that plate because of distance change, this is doing it. The distance isn't changing, but the area is changing. So that's another device there. And if you're interested in any of these devices, I once again recommend the MST Club. And I never can remember what that stands for, the Microelectronics Systems something or other. It gets you into the fabrication facility on campus and lets you build some of these devices. Again, this is very small. You might want to amplify it, but this is, gyroscopes, accelerometers, use some of this technology, and other ways of making those capacitances. This whole centerpiece right here is like a diving board, and here are the plates on the outside there, and it moves around and does capacitive coupling with the bars. Same effect as the previous circuits. I believe this one actually, the way the spring is set up, it rotates. But I'm not sure about that. All of these slides right here have references, so if you're interested, you can go look at these. If you don't know how to do that, go to the, library.calpoly or libcalpoly. You go to the library link, you go to databases, you go to IEEE, and then you search in there by topic. Okay. And some more other ways to make your springs so that one plate of the capacitor will move. Okay, so those are all things that need a lot of amplification. And again, the cell phone doesn't need so much. Needs a lot when it's receiving, but when it's going out to a speaker or something, it doesn't need all that much. So we've already seen this, but one more time, let's review how you can think of this as an inverter. This is the exact same circuit as you saw in 307 for a resistor transistor logic inverter, but in this class it's going to be an amplifier, and the only difference is no difference in the circuit. The only difference is where what part of the transfer function we use. What part of the transfer function we look at. In digital, we look at the ones and the zeros. In analog, we look at the region where the signal is changing. In digital, you hate that region that's changing. In analog, the regions that are ones and zeros are boring. Okay, so let's look at this. Here we've got a switch that closes on high, which means when you give it a voltage that's high on a third terminal here, this connects these two wires and basically connects V out to ground. When this is open, it cuts this wire, and now basically V out is connected to the supply through a resistor. So when you're trying to figure out what a circuit does, it's always good to look at the extremes. So first, let's say that's what happens when Vin is 0. Okay, when Vin is 0, the switch is open here, this wire is cut to ground, and this is basically connected to V-sup through a resistor. Since consider this as not connected to anything. So no current's going to go through here. If no current's going through here, there's no voltage drop. It means V out. V's up, and you've got what happens when V in is small. So this is the transfer function we're creating right here. On the x-axis is the input, on the y-axis is the output. Okay, let's look at the other extreme when V in is large. When V in is large, switch closes, and now V out is connected to ground through a wire, which gives you low. Now when this is connected to ground, that means that this side of the resistor is ground and you've got current going through here. Means it's using power. If the larger you make your resistor, the less power you waste when V out is low. Okay, question becomes what happens between here, and the answer is it's really hard to calculate, so usually just draw a line when we're sketching it. And looking at this, and over here, you've got a nice 1, here you've got a nice 0, that's where the digital people are happy. For analog, if you look at the gain here, the change in V out is 0. Remember, gain is the change in V out over the change in V in. So when V out is 0, that means the gain is 0. That's not very interesting for analog people. But here, when you change V in, V out changes. That's your amplification region. That's what you use for analog. Okay, you say, all right, well, this is an inverting amplifier because when I increase V in, V out decreases. So let's see, what if I flip the switch? What if I move the switch up here, invert it, basically do, if you recognize that this is how an NMOS works, or an NPN works, give it a high input, it closes and connects V out down here. So what if I flip this circuit, like we did in class? Does the graphs flip? So let's look at that. All right, now we've got PNP device. So when I give it a low voltage here, that's when this conducts. So let's see, when it's low, this closes and connects V out to supply. When it's high, this opens, and now V out is connected to ground through a resistor. Okay, again, when you're trying to figure out what a circuit does, it's good to do extremes. So let's try V in low. When V in is low, this closes, V out's connected to supply. Okay, when V in, now for the other extreme, when V in's high, this is open, V out is connected to ground through a resistor, and you get low. Same circuit. Turns out that transistors, these circuits are naturally inverting. So even if you flip your amplifier, now since we're in analog land, I'm calling it an amplifier now, but you could call it an inverter. It's going to be the same graph as the previous slide, whether you have the switch down here or the switch up here. Okay, and so that's the end device version that we saw, and you've had practice flipping the circuits. Source, okay, and then in the analog world, these are very well-known amplifiers, and to find the name, easiest way to do it, you can remember other rules, but if you just look at, recognize this as a 3-terminal device, and you look for V in and V out. So V in's on the gate here, so cross out the gate. V out's on the drain, so cross out the drain. What's left? A source. So this is a common source. Over here, base has the input, collector has the output, emitter, the common emitter. The leftover terminal is a common emitter. Okay, and so you say, well, what is this one called? Let's figure this out. Here's 3 terminals again, but it's a PMOS now. Okay, gate, cross out because it's V in, drain, cross out because it's the output. What's left? The source. So this is also a common source. What about the PNP? You look at the input. Input goes to the base, so the base is crossed out. Collector has V out, so collector gets crossed out. What's left? Emitter, common emitter. So it doesn't matter whether you, you build this circuit with an NPN or PNP, they're both common source amplifiers. Okay. All right. So let's do a little bit of Bosco here. You've got this great amplifier here. Here's your transfer function. If I stick a resistor out here, I just picked, since it was on the homework, picked this circuit right here. If I, let's see, right there, that's your transfer function. If I take that output and I put it into this other circuit right here, I use it as the supply to this other circuit right here, will your transfer function look alike? Look the same as it did before you put that circuit, connected to that circuit? The answer is, from the homework, hopefully you know that there's some current's going to go out there, the behavior is going to be different, and you'll get a different transfer function. Okay. And this is called loading. Okay, so that's the answer to the rest of the quarter. Well, not the rest of the quarter, just for a few weeks. That's the answer. There's some other type of amplifiers that I'm not going to talk about in class. Some linear amplifiers, and we'll talk about why linear is good in a second. Power amplifiers, I believe that's covered in one of the power device classes, but I'm not sure. But just know, again, I'm trying to remind you that we're ignoring so many different kinds of amplifiers that just know they're out there, and just know that we're not doing all amplifiers. We're doing one single type of amplifier, the operational amplifier, in this class. So just describing amplifiers, this RN and R out, again, that we have, it's hard in this class, just because if you want to talk about the topics that are being talked about in the lab, at the right time in the lecture, then you have to fall behind on some other topics. And so what I've given up is this calculation of RN and R out. We'll get to it very soon, but I just keep mentioning it without the math behind it. But it exists, and you can set it, and we'll figure out how to calculate it soon. But remember, I mentioned with Bosco that if you have a voltage divider going to, say, the input of a BJT, since there's a base current, some of that current gets stolen off of the voltage divider. The Rin of the BJT, Rin tells you how much current is going to be pulled off of that voltage divider. So Rn is very important when you're trying to connect two devices together. And again, the R out of the previous device, if it's very small and the Rn of the next device is very large, then things are good. I feel like I'm talking about this Rn and R out without context, so I apologize for that. But just think Bosco. Forget about transistors if that makes it confusing. Just think about if you have the output of a circuit going into a big resistor, is more current going to go out of that first what did I say, voltage divider? So you have a voltage divider, and then you put a big resistor over there on the output. Less current's going to want to go out than if you have a small resistor out here, and more current's going to want to go through that. So that's the way to think about it. I would really redo this video and not talk about Rn and R out so much if I had the time. Okay, gain is something. So these are all things that are important to talk about when you are doing amplifiers. So your Rn, R out, gain, where you can swing your input. In the last lab, you probably found that if you didn't swing the input in the very right place, well, that's not true since you were doing an AC coupling cap, but if you didn't have that AC coupling cap and you had it that connected directly to the input of a common emitter, you can imagine that if you have your input swinging too high, it's going to just cause so much current, bad things will happen. If you have it too low, your transistor's in cutoff. So where you can put your input and still have your amplifier works, that's very important. How much your output swings, that's important. And then various issues that have to do with noise that we'll talk about later. Okay, so these are the important values when describing an amplifier. We'll come back to these in about 5 weeks. Okay. Metrics, again, gain is a change in V out, change in V in, so it's the slope right here. Since it's rise over run, V out is already the rise, V in is the run. It's different than when we're doing that VCE versus IC graph. You had to take the inverse of the slope to find your R out. Right here it is the slope. Okay, and now here's your input swing and here's your output swing. Okay, this is an amplifier with not much gain. This is an amplifier with a lot of gain. If you look at these two, for us, we like a big gain because we're trying to make an op-amp, so we like this better, clearly. Now the input swing is just this wide. Okay, over here, the input swing can be that wide. Okay. So that's something you trade off with. Bigger gain means you have to be much more careful about where your input is. Nice thing is later in the quarter we'll be using feedback, and feedback does the calculation for you. It figures out where VN can be and fixes the input so it fits right in that little region right there. So you can have a really big gain. With feedback, it'll put the input right in that band that it needs to be in the amplification region. Without feedback, though, this would be pretty tough to get VN right between there and there. Let's see. So yeah, so we like this big gain because that's what we're trying to do for this class. We're trying to make an op-amp. But it turns out with this big gain, now we've just made a better digital circuit. There's more 1 and more 0 and less of the undefined region by making it a bigger gain. So if you can make a circuit with a bigger gain, you've just made a better digital circuit. Yeah, okay. Put swing, amplification region. All right, so we talked about linear amplifiers. You know, you hear. That's it. Okay, let's go back to operational amplifiers. In the definition of operational amplifiers, all it says is the gain has to be big. All it says is the gain has to be big. It doesn't say anything about linear. And it turns out you don't really care. As long as the gain is big, you don't care if your operational amplifier is linear. But there are cases where you want a linear amplifier. And guess what? We're not going to talk about them in this class, but just to give you a picture of what that means is if this is a picture and you want to make it twice as big, you take every point on here, you maybe take a center point, and every point you make it twice as far as, so you have this point right here. What you do if you want to double the size of this, you take that point and you place it out here. And you'd have, okay, and you'd have, whoops, not quite sure where that picture popped up there without the second one, but yeah, but you'd move every point twice as far from the center. Okay, and what that looks like with your amplifier is that this slope right here, when you're talking about a linear amplifier, what you're saying is every voltage, if you move from V1 to V2, you've just, this change in the input has just been multiplied by 2, and that's the change in the output. And that could be here, it could be here. You'll see that times 2 any place you go. So if you put a signal in, it just gets twice as big. Not quite sure why that is there. and here's your twice as big picture. Okay, but it's pretty hard to make a linear amplifier, and you get some kind of curve or something. So maybe from here to here it's 2 times, but from here to here it's 1.5 times. And then your original signal that's coming in gets distorted a little bit, and rounded or stretched, or all these pictures here show you a distorted picture, and all that means is that you pick that center spot, and some of the points you move twice as far, some of the points you move 1.5 times as far. Okay, let's look at the actual definition of distortion here, and this is another piece of the definition of small signal. So this is another piece of the definition of small signal. So far what we've said is it needs to be in a linear region, and that's what this is what the next I think 2 slides connect you with. The other thing is that small signal has to be the change in something over the change in something else. So let's look at this. Here's our transfer function. Okay, here's the input. If I give an input of a sine wave like this, since this is curved, notice up here it's a little curved. Right here it's nice. It's a nice line, and then it's curved down here. If this signal right here, like this point right here, if you go up, hey, you're in that curved region right there. So this is not a linear amplification up here. Right here this is all a linear amplification. Oh, down here it's not a linear amplification anymore. So if you take that signal, it gets a little bit messed up. And you can see like this kind of flattens out here because it doesn't get amplified as much. Kind of gets rounded. Kind of looks like this, but the extremities are kind of distorted a little bit. Okay. From your signals class, you've probably been told that any periodic signal can be represented by a sum of sine waves. So, or cosine, sine, cosine. So this is representing, this is just a sine wave. Okay, it's sine of some, sine of omega t, or ft, or whatever you want to call it, with some amplitude. Okay, this over here, since it's slightly distorted, but it's still periodic, it can be represented by the sum of some cosines with each with their own coefficient. Okay, so that should have come from your signals class. Okay, so now if you take the Maclaurin series, which is a Taylor expansion around 0, whatever it is, you get a polynomial. Okay, you've got your constant term, and then you have your on each of your, since you're doing it around 0, you get, geez, I wish I had time to redo this video, but yeah, you get this polynomial. Yeah. All right, so if this is a complicated wave, you get exponential terms out to infinity. Okay. And humans don't like that. All right, humans, when you see a curve on a graph and somebody says, is this exponential? You say, well, it kind of looks like it's exponential. You can't, it's hard for us to deal with curves and complicated graphs. What we can deal with is lines. We like lines. And the math for lines is easy. It's just, it's human friendly. Okay. So if you look at this equation right here, if you got rid of from this C2 term on, right there, that's an equation of a line. That's an equation of a line right there. And it turns out that if you are in this linear region right here, these coefficients, C2, C3, all of these ones that describe the curvy part of the line. So up to here, this just describes the linear part of the line, and then these terms out here start to describe the curvy part of the line. If you are in a really linear region like this right here. Turns out C2, C3, C4, all the way out to C infinity, those are very small. Those are very small. These are the dominating terms right here. So what small signal analysis says is, well, we want to give people a way to do calculations on paper. We know people don't like polynomials that go out to the infinite order. So what we're going to do is we're going to, just the math is too hard, we're just going to stick in a region where the C2, C3, those are kind of small. And that region means that, gee, this line has to be kind of linear right here. Okay, so again, to make the math easier for humans, and really all the small signal analysis that you do on paper, it's all going to be in a region that is pretty linear right here, so we can throw out the rest of these terms and not have too much of an error. We'll still have an error because these C2, C3 are not zero in this region here, but again, just like the current equation is an approximation. It's useful, so we can on paper do some calculations and kind of see what our circuits are going to do. Yeah, it's an approximation, and here too, what we do is we say, okay, let's get rid of those. We understand this equation, V out equals a constant plus a constant times V in. That's a line, we understand that, we can do math on it. That's what small signal is. Small signal is where you throw out the rest of these, which means you have to be in a linear region here. Okay, so what do we have for small signal definition now? It's in a linear region of the transfer function, just so we can throw out these terms. It's a change in something over change in something else. And we'll get to the very last part of that definition on the slides after next. Okay, and you may have heard let's go, of harmonic distortion. Okay, harmonic distortion is just, remember that constant on the squared term and that constant on the linear term? It's just a ratio of those times 1/2 times your signal amplitude. Okay, so harmonic distortion, all those, remember that, let's go back, this equation right here, harmonic distortion, all of those other distortions, they come from the ratio of these coefficients here. Okay. All right. This is really not connected to anything, but this is what an electric guitar sounds. Those are just clipped sine waves, and really this really has nothing to do with anything. All right, so that is amplifiers, the big picture. The summary is you don't always want a giant gain. Depends on what your application is. For us, we're doing an op-amp, so we want a giant gain. Other things are, you can have a voltage in, voltage out amplifier, current in, current out, voltage in, current out, current in, voltage out. Those all have different names. You can have a differential input or a single-ended input, differential output or differential outputs, a single-ended output. And they all have their applications and uses. It's just that in this class we don't have enough time to do them all. And I think that's it for that topic. Not sure how long this has been recording, but let's see if we can just add this other. Let's see if we can get through this in a reasonable amount of time. Okay. So you saw in the last lab when you had your amplifier, got it all biased up so you had the right current through it, and then you wanted to put a signal onto it. You used an AC coupling cap. We haven't really talked about the various applications of capacitors or inductors, so that we're going to talk a little bit about that. Also just go quickly through 4-resistor biasing. You've probably already have no problem with it, but just a quick calculation of it. Okay. Once again, you want to be in active. It's actually, all right. I know what I'm doing here. Okay. So this is a picture of your amplifier that you did in lab, and this is your biasing voltage right here, and this is that AC signal that you put on top of your biasing. So this is, you have a V in across the capacitor. That moving signal part, that's what this is right there. And the thing that the voltage that the base sees is the sum of the two. Your biasing voltage plus that voltage that's put on top of it through the AC coupling cap. Okay. Sometimes in lab, and you've already been doing it, I've seen everybody already doing it, but just to remind you, sometimes in lab you want to do a sanity check on your circuit. You want to make sure that it's in the region of operation you want it to be in. You already know that this is about VB on right here. You know this voltage, for it to be in the active region, V out has to be above VC sat. You know that before you put the signal on there, you have some biasing voltage on there that puts a current through here. So you need to make sure that with that current, it doesn't put V out so low that your transistor goes into linear. Yes, so that's what I'm saying here. Is that, yeah, with that current across the resistor, V out has to be above VC sat. Okay. So large signal analysis is what we've been calling biasing, and that's putting the DC voltages in, for our circuit it's a voltage, but it could be a current, onto your transistors to make them operate in the region of operation that you want them to be in. So let's just do it once for a 4-resistor biasing circuit. This is in the ABET required topics, so we have to do it once this quarter. So we will do it right now, though we don't really use it in lab. Okay, so let's say you know that you want to bias your transistor using the 4-resistor biasing technique. First thing, it's always good to figure out what you know. And I think you know this VBE. All right, so you know that VBE, but all of these resistors you don't know. So what you can say is that, oh gee, if I know either one of these voltages, then let's say I know this voltage, then I know this voltage is VBE on below the base, and hey, now I know the voltage across this resistor. If I know the current, now I can calculate off R4. And if I know what this voltage is, now I can calculate R1 and R2. Okay. Or you can say, you can pick a voltage for this, and then you say, oh, well then I know the base is VB on above it, and now you can figure out R1 and R2. So you have to either pick this voltage or this voltage to start off with. Okay, and current, either way, current is the most important thing to pick when you're designing. It's the thing that runs down your batteries. It's the thing that blows up your circuit. So that's the first thing you should always pick. And then you pick, again, the emitter or base voltage, not 0.7. You go to the model file and find VJE, and that's your VBE on. And then if you know the emitter voltage, then you can find your R4. If beta is small, then you want to include it in your equation. And yes, okay. We picked our IC, and we know that you have your IE is your IC plus your IB. So that's what that is. Okay. All right. And then once you have that, once you have the emitter voltage, you can find out the base voltage, and from there, it's just a voltage divider to get that voltage that you expect. But if your beta is low, you have to take this current into the base of your transistor into account. And that's Bosco. That's Bosco. That's loading. You've got your voltage divider here. Some of the current is, a little bit of current is going to be going out through this wire right here. So you can't just say, oh, I want this voltage here and pick R1 and R2. You have to take into account the current that's going into the base there. Once you have that, you just know that you'd like this. If you don't know, I don't have the input on here, but there would be an AC coupling cap right here, VN, putting the moving signal on top of however you biased your base voltage here. So an AC coupling cap to put the moving signal on top of the voltage that the voltage divider sets here. Okay. Then if you don't know what your V in is, it's always nice to put your V out kind of in the middle of the range that will keep your transistor inactive. So you find out the lowest V out can go and the highest V out can go, and you want to put your voltage kind of in the middle of there. And then if Vn goes up, if you put this in the middle of that safe range, then V out can go up as much as it can go down, and that accommodates the largest variety of input signals that somebody could give you. So even if you don't know what V in is, if you bias V out so it's in the kind of the center of the legal region, then it's safe for the most different types of VNs that you can get. Okay, I'll let you look at these calculations because you've done it in previous classes. Okay, and all these slides are up with the animations, so you can see the calculations that I did. Okay. Okay, so again, if you remember what you did with your amplifier, first you set your current through your amplifier, and then you put your moving signal on top of it. That's absolutely the way to build your circuit. You always want, when you're building the circuit, you always want to check the DC voltages first, voltages and currents first, and then after you've checked those, then you put the moving signal on and check them. Those DC voltages and currents, those are called your large signal values, or your bias values. Okay, we'll come back to this a later time in the quarter. All right, and then this is the actual steps for the math, so if you want to go in and check that there. Okay, that was from a previous quarter that I didn't delete. Okay. Let's look at a couple of other functions of capacitors. Let's put this on the next video. I think this is getting a little bit long here. Let's see, I think actually these are the last few slides. Alright, so let's keep going on this. Alright, so when you built the 4 resistor biasing right here, you had this resistor down below the emitter. This resistor right here, you probably looked at it and said, oh, degeneration, that's a degeneration resistor. It's actually not. It's setting the voltage at the emitter. If you remember how you calculated that, you calculated that for a DC value. So this is a biasing resistor. It's not degeneration. So if it's trying to set the voltage at this node, when you're operating your amplifier, you don't want this node to move. If that's a bias voltage, you want it to stay constant. So what you can do is this capacitor right here. It's called a bypass capacitor, and you put it in parallel. You put it to a bypass capacitor is connected to any node that you don't want it to move. So let's see how it keeps this node from moving. So a bypass capacitor keeps this voltage from moving. The way it does it is when you change this input here, you get a current change through your transistor. So when you change the base voltage, you get a current change through this transistor. If that current change through the resistor right here, if that current change went through the resistor right here, this node would move around. Okay, so you move the base, change in current. If that current went through this resistor, this node would move. And remember, this is a biasing resistor, so it's trying to set a voltage here. So you don't want that to move. So what you do is, if you put a capacitor in parallel, it gives that current an alternate path to go through. If you make this capacitor really big, when you change your current, it's all going to go on and off of that capacitor. So it takes a lot of current onto that capacitor to change the voltage. Okay. So if you make a big capacitor, a lot of current has to go on there before the voltage changes. If the voltage changes across here, yes, a little bit of current will go through here, but the majority will go over onto this capacitor. It's like you have to fill up that lake before the voltage goes up. Okay, and you can do that. I mentioned a couple times earlier in the quarter that when you run digital circuits, sequential circuits, that current every time the clock ticks, a bunch of electrons get thrown onto the supply, and a bunch of electrons get pulled off of ground. And if you pull a bunch of negative things, so electrons are negative, if you pull a bunch of negative things off of ground, ground becomes more positive. And then if you dump those negative things on the supply, which is positive, it becomes less positive. And so you get the supply, you've always taken the supply as just 5 volts sitting at 5 volts ideal, and you've always taken ground as sitting at ground and never moving. But what actually happens is every time the clock ticks in a digital circuit, those things bounce around like mad. Okay, and so you can actually solve that problem by using bypass capacitors. If you put a let's see if I hope the next slide is. Darn it, where's that slide? Okay, what you can do is, so here's some sine wave. In our case, we can think of it as a sine wave, but in digital it would be, ones and zeros changing values. You'll see that on the ground. It'll be affected on the ground. What you can do is you can add a bypass capacitor, and I'll show you where in a second, and it will flatten out your supply. This is the supply voltage right here, and the purple is before you had the bypass capacitor on there, and the pink is after. Well, this is a board I built before I came to Cal Poly, and we used a Xilinx chip on the board, and all of this stuff around here, those are all capacitors. I think there was like 400, 600 capacitors that we used on the supplies to keep the supplies quiet. So we have analog and digital on the same board here. That's not exactly why this chip it was so noisy that in order to keep VDD and ground quiet enough for even the chip to work, we needed this many capacitors. And there's capacitors on the bottom too. These are all surface mount capacitors. But let me draw a picture of that. Okay, so let's say you had this supply, and then some circuit. Here's some circuit, and here's ground. And this circuit was really noisy, and it was putting noise on the supply and ground. What you can do is, so these are 2 wires. Anywhere there's a wire with DC on it, if you put a bypass capacitor on it, and the closer it is to to infinity, which you know you can't get, but the larger it is, the quieter VDD and ground will be. So you can connect VDD to ground. They're both DC, so you can connect them with the capacitor. This will be a bypass cap. When this needs more, when a bunch of electrons gets dumped onto there, this will absorb some of that bounce. Same thing here. When a bunch of electrons get pulled off, this will absorb some of that bounce, and it'll quiet your supply down. Okay. Okay. We'll skip this. We haven't talked about inductors at all. You really don't until you get up to really, really, really high frequencies. So it's not going to come up in this class again. But if you have noisy ground and supply, you can put an inductor in series, and that'll let the DC through, but block off the AC, the moving stuff, the noise that's on VDD or ground. And this is called a choke. This is a choke. Okay. So you have a bypass cap to quiet DC nodes. You have an AC cap just to let the AC signal through, but not the DC. That's the one you used for putting a signal on top of the biasing voltage in your last lab. And you have a choke, which puts ground on this node and VDD on this node. Okay, we're skipping that. This is a a low noise something or other, but you can see that there's inductors every place to keep DC values at. So this right here would keep this at this voltage. This inductor would keep this node at this voltage. Same thing here. This would be VDD. This would be close to VDD. Yeah, this is the last part of the small signal definition, and we'll come back to that in a couple slides. Okay, so almost there. This isn't from last lecture. These aren't the updated slides. The Ham Radio Club wanted to connect the EE building with the administration building, and it turns out their ground is 50 volts different. Remember that AC capacitor? That right there, that's a bad idea right there. If your grounds are 50 volts across apart, you really don't want to connect their grounds directly. You'll get massive amounts of current. Yeah. Okay. Enough said. But if you do that, then the moving part of the signal goes across the capacitor, and everything is good. Okay. Okay. So one more time. This is your AC coupling cap. There's an AC bias cap, and what's that? That's an AC coupling cap. Okay, we did that in lecture, and we're going to skip that. Okay, so these are the ideas for this lecture. Biasing, setting a current through a circuit, bypass capacitors to quiet DC nodes, AC coupling caps to let the moving signal through but not the DC, and then chokes, that's your inductor, to protect against noisy supplies. And that's that. I'm gonna, let's see, the next video will be, I think I will make it shorter since this one became quite long.